All right, I got another question here. This is, let's see, chapter 36, number 48. And this one is kind of talking about a telescope, but it only talks about the objective piece of the telescope. So the first set of optics, either a mirror or a lens, and not the eyepiece. And it says up here, question A says, show that the image height, so h prime, for such a telescope is given by this equation, the focal length times the height of the object over the focal length minus the distance to the object. So this has got a bunch of algebra in it, but I'll start with 1 over p plus 1 over q equals 1 over f. And let me emphasize, in chapter 36, it's this equation and this equation minus q over p, which is the height of the image compared to the height of the object. So this is called the magnification. And then this is called the lens equation. And so it's these two that really kind of determine everything about our geometric optics. In fact, let me use this as a chance to say, would you like to know the answers to every homework problem in chapter 36? This is it, because this works for both the lenses and the mirrors. And so that's why this telescope one says it doesn't matter whether if the objective, if it's an objective lens or an objective mirror, it would still be true. And then this would also be true. Now, in order to solve this, let's do the following. Let's leave 1 over p alone here, and let's substitute out this q. So I could write q then, and I'll move the negative to the other side, and also move the p to the other side. So that becomes 1 over negative h prime over h times p equals 1 over f. And so now we have an equation that is going to look like what we're trying to show, which is this, because it has no q's in it. And that's how I eliminated, using this equation to eliminate the q. And so now I just got to solve it for this h prime. So I'll start with the 1 over p. I'll put the h and the p on top. Minus h prime equals 1 over f. And then eventually to solve for this h prime, let me just move the p, 1 over p, to the other side. Let me note that this has a common denominator of f times p, so that means I got to multiply this fraction by a p and this fraction by an f. And so then I can do the upside down theorem. Upside down, so I gotta flip it. So this is this, I think I gotta, I'm sorry, I think I messed up here. This was times p, so this should have been down here. And so that would put it up there. Okay. Yeah, let me just check that math here. So h prime, would be the h prime. Okay, all right. So so I'm gonna flip that minus h prime p over h, and then also flip this, and so this is an f p, and then this is a p minus an f. And then, of course, there's a p on each side, so they can cancel off, and then we can move the h over to here. And so we finish off, and then move the negative over. And so we have our h prime equals, and so we've got the minus, we've got the f, we got the h, and then we've got the p minus the f. One more step here, I guess, is to move the negative downstairs and then run it through with the distributive property so that this becomes then an f minus a p, and then lo and behold, we've answered part A. And so here's our equation for what does H equal. And then it goes on to say, okay, well, look at B. It says, we'll simplify this a little bit. It says, simplify this expression in part A for the case in which the object distance is much greater than the focal length. And so, very true for a telescope. Usually for a telescope, you're looking at something really far away. And, this is, at close is an orbiting satellite, but it could be the moon, or it could be the sun, or it could even be a whole nother galaxy. So this tends to be really big, and the focal length is, some, telescope, so it's something on Earth. A lot of our lenses have, 10 centimeters, but even a big telescope, just has it in the meters. Anyways, bottom line is when you are putting these two together, you pretty much could ignore the size of the focal length. This is just so many order times bigger. And so what they're saying here is you can simplify this by just writing it as the focal length times the height of whatever you're looking at divided by the object distance, and I'll just move the negative upstairs. And so this would be really kind of the same thing as that, given the kind of numbers we're talking about. We can just ignore the F there, which then is why then this last part says in C, it says, let's look at, the wingspan, that is the size of the International Space Station, and they're asking this, what would be roughly the size of the image if we were using this telescope to maybe take a picture. And so instead of using an eyepiece, so we look at it, we'll remove the eyepiece and put a camera there, and there's either a CCD array or an old-fashioned film. And so we're going to put that on it. And so how big does the piece of film need to be? How big is the image going to be on our photographic film? And so I'll put in the minus. They say here, find the width of the image of a telescope when the objective focal length is 4 meters. So I'll put a focal length of 4 meters. And H is the size of the object you're looking at. And they say this is 108.6 meters. So there's how big the International Space Station is. And, of course, how far away is it? And they say it has an altitude of 407 kilometers. Let me write that as meters so my units match up. And so we're going to get the height of the image on our film here in units of meters. And so grabbing my calculator here, I have a 4, and then times the 108.6, then divide it by the 407, 3,000, and so this would be 0.00107 meters, or 1.07 millimeters. And so the image, I guess there's a minus here, so that's going to tell me it's going to be flipped around, so the image is upside down on my photographic film, which is fine. I mean, it doesn't really matter. I'll just turn that over when I want to look at it. But this does invert it. In fact, a funny story, I remember years ago getting into telescopes, and I took a photograph of Mars, and there was a small moon that what I kept saying was the 7 o'clock position, and that was in my photograph. It was really in the 1 o'clock position. So I had a buddy looking through the telescope, and I kept saying, look at the 7 o'clock position. No, I don't see any moon. You can barely see it, but it's there. No. And then finally realized, wait a minute, look at the 1 o'clock position. Oh, yeah, I see it. So anyways, we got to remember that they inverted, and that's what the negative is saying here. And so that's it.